In order to be able to store information in the hash table, we need a hash function. So the hash function is what we will use to translate, say, the person's name or some integer or some floating point value into an actual index location in the underlying storage table. So the assumption we'll make here, just to be consistent throughout our examples, is that data is stored in a contiguous table, something like an array, which holds m items. So throughout these slides, we will refer to m as the size of the table, the number of elements present in the table. So the size of the hash table sort of becomes part of the solution and can greatly impact how a particular hash table functions. We select the table size m by usually picking a very large prime number or a non-prime number that has no prime factors below 20. And then we index the items into the table. Obviously, the index locations would be 0 through m minus 1 for m items. And then we'll just store them in the table. So the way that this is different from an array is the notion that, for instance, when based on my hash function, the value 26 can go anywhere in my table. It need not go into index location 26 in the table. And we can place it anywhere based on the output of the hash function. Now, so the hash function then is what maps our data to the particular table index. It should be easy to calculate because you need to do this over and over as you store items into tables. And we're going to see that we will also need it to retrieve items, to delete items, and various other operations. So it should be simple to calculate, but the more important aspect is that it should distribute the keys uniformly over the table's index range. So what we mean by that is if I have an underlying table of 500 items, I don't want my hash function to continually try to insert items into elements 100, say to 350, because that region of the table will be really full and other regions of the table are not getting any data items. So we need to make sure that the hash function we pick will actually distribute the keys fairly uniformly across the indices of the table. Now, we also need the fact that H transforms needs to be able to transform every key that we could possibly put in the table, and it needs to be able to come up with a location for every possible key. Now, if we can do this, if the function h, which is our hash function, if it can do this so that every possible key maps to a different location, okay, so we're talking about a one-to-one mapping of keys to index locations in the table, this is said to be a perfect hash function. Okay, so the hash table in this case would have to have as many elements, as many slots as there are keys that we intend to store. In reality, since we don't always know how many keys we will have, and since we don't always have a detailed distribution of what the key values will be, we will not always get perfect behavior out of a hash function, and so at best we can only approximate it. Now let's take a look at some common hash functions So most hashing methods will involve the modulo operator, okay, the percent sign, the remainder operator, in order to calculate a valid table index. So whatever we calculate for the hash value, we will eventually do what's called normalizing that value by modding it by the table size. This will give us index values between 0 and m minus 1, with m being the table size. So this approach works well if we actually don't know what the data is going to look like. So we don't know what all the keys will look like. This is a good approach. So let's take a look at some common hash functions. So the direct key modding is probably the most basic hash function. So what we'll do is if our key is an integer, we're just going to take that key value directly and we're going to mod it by the table size. So as an example, if our key value, so if we're trying to store the value 511 and we have a storage table of size 367, okay, which is a large prime number, then we would map that particular value to index location 144 in the table. That's 144. How did I get that? I take my 511, which is my key value, and I mod it by m, in this case 367. That gives me a remainder of 144, and that is where I place this particular data item. Now that's all well and good, and that works for integers, but a lot of times, for instance, we want to convert floating point values, or we want to convert, say, strings. Strings are often stored in hash functions because last names are often a key value that identifies someone. Phone numbers, for instance, oftentimes you'll go to the store and they'll ask you for your phone number. And so they're probably, the underlying system is probably calculating a hash to retrieve your information and your shopping history. So if we want to take strings, for instance, and convert their values so that we can place them in a hash table, then one of the things that's available to us without doing a lot of deep thinking is to actually take the ASCII values of the individual characters, add everything together, and then again, we have to mod by the table size. That last step, as shown up here in this first sub-bullet, that last step is important because that's what's going to translate whatever the hash function returns to an actual index of the table. So for instance, going back to our string example, if we have the string data with a capital D, then we can extract the ASCII values. Capital D is value 68, lowercase a is value 97, lowercase t is value 116, and then lowercase a again is 97. If we sum all that up, we get the value 378. And if we have a hash table of our large prime number, size 367, then we would store our data key. It would map to index number 11, which is the 378 that I came up with, modded by the table size. So my hash function in this case takes individual ASCII characters and adds them together. That's the end of the hash function. Okay, so if we look again back at this top sub-bullet, h of k in this case yields the 378. And this second step is called the normalization step, and it takes h of k and mods it by the table size in order to actually get an index position to where to store that data. Okay, so in this case, our string capital D, lowercase ata would map to index 11 in this particular table. Okay, here's some other methods. For instance, we can do shift folding. Okay, shift folding is generally when we take a particular key and we split it into some parts. The parts need not be the same size, but a good example is a social security number, which has 9 digits, and we may choose to split it into 3 equal parts. And so if the social security number was 1, 2, 3, 4, 5, 6, 7, 8, 9, we could subdivide it into chunks 1, 2, 3, 4, 5, 6, and 7, 8, 9, and add those together. And so this is our H of K. So our K in this case is the social security number. The hash function H, what it does is it splits it into 3 chunks and it sums them together. And then finally, the second sub-bullet is the normalization step, where we take our table size 367, which we refer to as M in this case, and we map that value, that 1368, we mod it by the table size, and it maps to index 267 in this case. Boundary folding is basically just a slight perturbation of doing shift folding. In essence, we will split into those same parts, but we will reverse, for instance, alternating parts. So that same social security number then would have as its middle component, instead of 456, it would have 654, as you see here. Okay, and then we add those together, and you notice that the sum of those differs from the sum that we saw earlier. So the sum in this case is 1566, and if we mod it by M, our table size of 367, this data would store to a different location. This social security number would store to index location 98 in the array, rather than index location 267 if we just applied basic shift folding. All right, so the combination methods here are not strictly restricted to addition. It actually turns out that most of the time this work is done in the binary world rather than actually using digits as ASCII characters. For instance, we can convert everything to binary and perform operations there. And so we will often combine with other methods. So folding, for instance, can be used by combining it, convert everything to ASCII, then fold, and then mod. So there are some different methods going on there. We're combining everything together and coming up with a location to store the data. Now, partial keys is one last common hash function that I want to cover. So it turns out that hash functions, this is a whole area of research, and people spend their entire lives sometimes studying hash functions to try to get good hash functions that distribute the data pretty much uniformly across the table. So I'm giving you some very basic examples of hash functions just to get the point across as to how they work. If we're looking at digits, for instance, we're looking at numbers. We only have 10 values at the end, and if we look at the last 2 digits, we only have 100 possible values. Those things tend to not change very much, so we can apply partial keys to extract some piece of information from the middle of a number or a string rather than using the end pieces. So in this example, in the mid-square example, the data we're trying to store is value 3,121, so 3121 here. And so we take that value and we square it. This is why it's called mid-square. And then we extract the middle part of it. So in this case, the middle part worked out perfectly because this particular thing has 7 digits, this square, but it doesn't always work out evenly. Sometimes you have 6 and you have to decide what that middle piece looks like. But in essence, we'll take those 3 digits in the middle, 406, and that now becomes our key. And then we will mod that value by the size of the table and actually get an index as to where to store value 406. So mid-square, along with many other hash methods like folding and boundary folding, are actually applied often to binary values rather than actual ASCII string number representations. Okay, so the last part I want to talk about is we can just extract part of the key. So this is called extraction. It's basically a partial key, right? So if I have a 9-digit social security number, I can just decide to take the middle 3 numbers, the last 4 numbers, the first 4 numbers. And there are some examples there as to what those values would be. And then I would take those values and mod them in some way to get an actual index location to store this data in the tree, in the table, excuse me. So the important thing here is, you know, you've got to be wise in how you choose these keys. For instance, social security numbers tend to be attached to regions of the country, the first few digits of a social security number. So you probably would not want to use that as your partial key, as you would have very little diversity, say in a particular state. The individuals would keep mapping to the same locations of the table. Okay, so we'll take a look at how to utilize these to store information in hash functions, in hash tables in the next block.